Okay, so now we're going to talk about analyzing the fragments, right? Remember, what we get is we get some compound and we take away an electron, we get the molecular ion peak, right? And then we take away another electron or the molecular ion fragments, and we get all these pieces, right? We also talked about the M+1 peak, and that happens because 1% of carbon is carbon-13, right? And 1% is equal to carbon-13. We also talked about the M+2 peak, and that was mostly because of chlorine and bromine, right? So, but now we're going to talk about the fragments, okay? So remember, if we get pentane, we first of all get the molecular ion, which is this. That's where one electron's been taken away. But then we get all possible fragments. So if, for example, this guy comes here and this guy comes here, then we're left with the M-15 peak, right? So we're not going to call all these peaks M-15, but it's good, I think, to keep accounting of it. So M-15, because this is 15, right? Or the M-29, because this way is 29, right? So remember in a previous video, we saw that the pentane mass spectrum, the most common peak, the base peak, was M-43. So it looks like that's going to be the most common fragment that we possibly get here. You can't tell by looking at it, by the way. Sometimes there'll be some things that are intuitive and sometimes not so. But when we look at the pentane mass spectrum, this is the most common peak. That was the base peak. So all of these things are going to show up. We're going to see an M-15, an M-29, an M-43, and an M-57. They're all going to show up if they're common enough, right? So we'll see. Now look at. Remember that it only detects charged fragments, so this is not going to be detected. We will see one with 4 carbons in it, but it's going to be the one that's charged, not the one that's not charged. We will see one with 3 carbons in it, but not that one. We'll be seeing this one here, right? So let's look at the mass spectrum then of pentane. And sure enough, I was thinking it was M-43. Maybe I'm thinking of a different spectrum that we saw. But here it is, M-29. So it looks like that's the one. Let me go back a slide. This is the most common one, right? That's the most common fragment that we get here. And so here it is. Look at that. Okay? And this is because carbon-13, right? 1% of the carbons in that fragment are carbon-13. And so here's the molecular ion peak. Wow, it looks like that's pretty uncommon. So it looks like pentane breaks up a lot more than benzene. Remember that one? So, but the base peak here is a fragment. It's the M-29, and it's the one with 3 carbons in it. All right, so we also get fragmentation of other things, of course. Look at this one. Suppose we have some compound. It looks like it's 2,2-dimethylpentane, right? Can you see there's my pentane? Right, 2,2-dimethylpentane. So if this breaks up, then we're going to get different things. So here's one with 43. There's a tertiary carbocation, which happens to be very stable because it's tertiary. All right. So this is what we have here. A tertiary carbocation is very stable, and so since that's very stable with 2,2-dimethylpentane, you can expect to see a very large percentage of them that are going to have 4 carbons in them because this is stable. So you are going to be able to make some predictions about mass spec, but again, we always have to make these predictions, I think, with some modesty. All right, so alcohols undergo fragmentation in a couple different ways. So we're going to see a stabilized oxonium ion. You don't have to memorize this. It's just explaining what's happening. Okay, so if we get, suppose we've got some alcohol, and one thing that can happen is we can take an away electron from here, right? And then we get, this is just some, it's resonance stabilized, and that makes this a very common peak, right? If we get alpha cleavage, if we get the elimination of that. So again, this is not something that you necessarily need to remember as much as it's an explanation, decent explanation. When you get stabilization of some fragments, stabilized fragments stabilized fragments are more common, or they show up, their peak is going to be bigger because they're stabilized. Okay? And so we can see that we might get something like an M minus 18. So this is an explanation. You're not going to be asked to show that, but it's a good explanation that, you know, when you get electrons shuffling around, you're going to get stabilized fragments. And those fragments, sometimes they're not going to be like obvious pieces of a molecule that you started out with. Okay? Amines also undergo some similar kind of cleavage. McLafferty rearrangement, we may come back to that at some point. A McLafferty rearrangement, because this is a little more common. But for now, I think I'm gonna blaze past that one also. And just to say that we get rearrangements sometimes, and so you end up with fragments sometimes that are a little difficult to appreciate where they come from. We haven't done carbonyls, so I can see we may come back to that when we do carbonyl chemistry in Organic 2. All right, so the presence of these characteristic fragments in a mass spectrum confirm structural features. If we have an M minus 15 peak, oftentimes that means we lost a methyl group. If we have an M minus 29, it means we lost an ethyl group. M minus 43, we lost a propyl group. Does that make sense? So, and then M minus X, or X is an even number. We're going to come back to that in Organic 2. But for now, you can see how losing different pieces, the fragmentation, is going to give you these kinds of peaks. What's the most important thing that we get from mass spec? Molecular weight, right? That's the M plus peak. That's the most important thing we get from it. The second most important thing we get from it, I would say, is the presence of chlorine or bromine because of the M plus 2 peak. All right?